Picture the universe in its infancy, a vast darkness stretching endlessly before the first flicker of starlight dared to break the silence. Why does this moment, when the cosmic dawn first painted the heavens, hold answers that could rewrite everything we know about existence? Hidden within those ancient stars are secrets so profound they challenge our understanding of time itself. How did these celestial pioneers transform a lifeless void into the glittering cosmos we see today? We're about to journey back further than telescopes can see, to an era when the universe was raw, uncharted, and teeming with mysteries we've only begun to unravel. The first stars weren't just objects in space, they were the architects of reality as we know it, forging the very elements that would one day become planets, oceans, and even us. Yet their stories remain locked in the darkness of those early cosmic ages, defying even our most advanced technology. What if the key to uncovering these lost chapters lies not in what we've found, but in what's still missing? By the time we reach the end of this exploration, you'll see the night sky not as a static painting, but as a living puzzle, one where every twinkling light is a clue to the greatest detective story of all. This isn't just about distant suns, it's about tracing the origins of everything, including ourselves. And the deeper we dig, the stranger the universe becomes. Now, let's pull back the curtain on the universe's very first starlight population, 3 stars. These celestial titans were unlike anything we see today, born from a cosmic recipe so simple it defies imagination. Pure hydrogen and helium, untouched by heavier elements, fused in their cores with unimaginable ferocity. Picture a star hundreds of times more massive than our Sun, burning so fiercely it lived and died in the cosmic blink of an eye. Their brilliance was unmatched, yet their fleeting existence is why they've remained invisible to our telescopes, ghosts haunting the early universe. We call them Population 3 because they predate even the ancient stars we've catalogued as Population 2 and 1. But here's the twist: despite decades of searching, we've never caught a direct glimpse of them. The reason lies in their tragic fate. Their sheer size meant they consumed their nuclear fuel at breakneck speeds, exploding in violent supernova within just a few million years, a heartbeat in cosmic time. These explosions scattered the first heavy elements into the void, seeding future generations of stars, but left no intact survivors for us to study. What makes these stars so alien? Without heavier elements to act as cooling agents, they couldn't fragment into smaller, longer-lived stars like those we see today. Instead, they grew monstrous, with temperatures and pressures so extreme they likely glowed blue-white like cosmic blowtorches. Their deaths weren't just spectacular, they were transformative. The iron in your blood, the calcium in your bones, all were forged in later stars that inherited the chemical legacy of these primordial giants. The hunt for Population 3 stars isn't just about filling a gap in our cosmic family tree. It's about decoding the universe's instruction manual. If we could find even one surviving relic, perhaps in the faint glow of a distant quasar's shadow or the unusual chemistry of an ancient galaxy, it would rewrite our understanding of stellar evolution. Until then, they remain the ultimate cosmic cold case, their secrets buried in the faint whispers of the cosmic microwave background or the distorted light of the earliest galaxies. But here's a tantalizing clue. Some astronomers believe the distant galaxy GNZ 11, which should have been too mature for its age, might carry the chemical fingerprints of Population 3 stars. Others scour the Milky Way's halo for elusive second-generation stars with barely a trace of metals, the closest we might ever get to touching the universe's first starlight. Every dead end only deepens the mystery, reminding us that the dawn of light wasn't just an event, it was a revolution written in fire. Now, let's step even further back in time to an era before the first stars flickered to life, a period so pitch black we call it the Cosmic Dark Ages. Imagine the universe as a vast, silent ocean of hydrogen gas, so dense and uniform that not a single photon of visible light could pierce through. This wasn't just darkness, it was the absence of light itself, a void stretching for 100 million years after the Big Bang. Why does this era remain one of cosmology's greatest blind spots? The answer lies in the very fabric of the young universe. Back then, space was filled with neutral hydrogen atoms so thick they absorbed any light trying to pass through, like fog swallowing a flashlight beam. Without stars or galaxies to ionize this gas, the universe was essentially cloaked in a cosmic smokescreen. Even our most powerful telescopes hit a wall when they tried to peer into this epoch, because the light that could reveal it, stretched and redshifted by the universe's expansion, now exists as faint radio waves buried in the static of space. But here's where things get fascinating. The Dark Ages weren't just an empty pause, they were a cosmic incubation period. During this time, tiny fluctuations in the density of matter, imprinted by the Big Bang itself, began to clump together under gravity's pull. These faint ripples would eventually grow into the first stars and galaxies, but for eons, they simmered in the dark, unseen. It's like trying to study the roots of a tree that's already fully grown. We know they're there, but digging them up without disturbing the rest is nearly impossible. That's where instruments like the James Webb Space Telescope come in. Unlike Hubble, which sees primarily invisible and ultraviolet light, Webb's infrared eyes are perfectly tuned to detect the faintest glimmers from this era. By capturing light stretched to wavelengths our eyes can't see, it might finally reveal the universe's baby photos, the moment when the first proto-galaxies began flickering on, one by one, like candles in the abyss. Some scientists even hope to spot so-called dark stars, hypothetical objects powered by dark matter annihilation, which could have lit up the cosmos before nuclear fusion took over. Yet the Dark Ages hold another clue to cracking this mystery: the 21-centimeter line. This faint radio signal, emitted by neutral hydrogen, is our best hope for mapping the universe's structure before light broke free. Projects like the Square Kilometre Array Radio Telescope aim to trace this signal like an archaeologist dusting off fossils, reconstructing the cosmic web in its infancy. If successful, we might finally see the scaffolding upon which galaxies were built, a blueprint hidden in plain sight. The irony: this era of darkness holds the keys to understanding light's origins. Every galaxy, every star, every planet owes its existence to the quiet gravitational ballet that played out in the dark. And as our telescopes grow more sophisticated, we're not just chasing shadows, we're on the verge of witnessing the universe's first dawn. Now, let's journey forward from that primordial darkness into one of the most pivotal turning points in cosmic history, the moment the universe finally woke up. Picture this: after 100 million years of utter blackness, something extraordinary happened. The first stars ignited, and their fierce ultraviolet radiation began tearing apart the dense hydrogen fog that had shrouded the cosmos. This wasn't just a flicker of light, it was a revolution. The universe was undergoing reionization, a dramatic shift from opaque to transparent, and it changed everything. But here's the puzzle scientists are still untangling. We know reionization happened, but the details are maddeningly fuzzy. Did massive, short-lived stars do most of the heavy lifting, blasting away hydrogen atoms with their intense radiation? Or were early supermassive black holes, devouring matter and spewing energy, the real driving force? The answer matters because it shapes our understanding of how the universe evolved. Let's break it down. The first stars, known as Population 3, were unlike anything we see today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously hot and dying young in colossal supernova. Their ultraviolet light was so powerful it could strip electrons from hydrogen atoms, turning neutral gas into charged plasma. Think of it like a cosmic defogger. Once the hydrogen was ionized, light could finally travel freely. Yet there's a problem. current models suggest these stars alone might not have had enough time or numbers to fully reionize the universe by the epoch we've observed. That's where black holes enter the debate. Quasars, supermassive black holes feeding at the hearts of early galaxies, emit staggering amounts of energy, far more than even the brightest stars. If they were common enough in the early universe, they could have supercharged reionization, punching holes in the hydrogen fog like a lighthouse beam cutting through mist. Timing is another headache. Observations of the most distant quasars and galaxies suggest reionization was mostly complete by the time the universe was around 1 billion years old. But measurements of the cosmic microwave background, the afterglow of the Big Bang, hint that it might have started much earlier. This mismatch has astronomers scratching their heads. Did reionization happen in fits and starts, with some regions clearing faster than others? Or are we missing a key piece of the puzzle, like undiscovered populations of early galaxies or exotic energy sources? The James Webb Space Telescope is now hunting for answers. By spotting galaxies and quasars from the reionization era, it could reveal which objects were most responsible for lighting up the cosmos. Meanwhile, radio telescopes like the Square Kilometre Array are mapping the lingering traces of neutral hydrogen, charting how reionization unfolded across space and time. What's at stake isn't just a timeline, it's the origin story of the universe we see today. Reionization didn't just clear the fog, it set the stage for galaxies to grow, stars to form, and eventually planets like ours to emerge. Whether stars, black holes, or both flipped the cosmic switch, one thing's certain: this was the moment the universe truly came alive. And the closer we get to solving this puzzle, the better we understand our own place in the grand tapestry of light. Now, let's turn our gaze to another cosmic conundrum, one that challenges our very understanding of how galaxies assemble in the early universe. Theory tells us the cosmos should be teeming with countless dwarf galaxies, tiny celestial islands orbiting larger galaxies like our Milky Way. But when astronomers peer into the depths of space, they find far fewer of these faint dwarfs than expected. This glaring mismatch between prediction and observation is known as the missing satellites problem, and it's forcing scientists to rethink everything from dark matter to the limits of our telescopes. Here's the heart of the mystery. According to our best models of cosmic structure formation, dark matter, the invisible scaffold of the universe, should have clumped together in countless small halos shortly after the Big Bang. These halos would then draw in gas, birthing swarms of dwarf galaxies. In fact, simulations suggest there should be hundreds, even thousands, of these tiny galaxies orbiting a single Milky Way-sized galaxy. Yet in reality, we've only spotted a few dozen around our own galaxy. So where are all the missing dwarfs? One possibility is that our telescopes simply haven't spotted them yet. Dwarf galaxies are notoriously faint, often containing just a few thousand stars compared to the hundreds of billions in a galaxy like ours. Some might be so dim they've escaped detection, lurking in the shadows until more powerful instruments can uncover them. Recent discoveries of ultra-faint dwarfs support this idea. Each new generation of telescopes reveals galaxies we couldn't see before. But there's another, more tantalizing explanation involving dark matter. What if these dwarf galaxies did form, but something prevented them from lighting up with stars? The leading theory suggests that early radiation from the first stars and galaxies might have heated the surrounding gas, making it too energetic to collapse into stars within smaller dark matter halos. Without stars, these failed galaxies would remain invisible to our telescopes, explaining their apparent absence. Alternatively, dark matter itself might behave differently than we think. Most models assume it's cold, slow-moving and clumping easily. But if dark matter were slightly warm, with particles moving faster, it would form fewer small halos, naturally reducing the expected number of dwarf galaxies. This tweak could solve the missing satellites problem without invoking unseen galaxies, though it would require rewriting parts of our cosmic playbook. The stakes are high because dwarf galaxies aren't just cosmic curiosities, they're critical to understanding galaxy evolution. These tiny systems are thought to be the building blocks of larger galaxies, merging over time to form the majestic spirals we see today. If our count is off, it could mean we're missing a key chapter in how structures grow in the universe. The good news, new tools are on the case, projects like the Vera C. Rubin Observatory will scan the sky with unprecedented sensitivity, potentially uncovering hundreds of hidden dwarfs. Meanwhile, simulations are testing whether alternative dark matter models can reconcile theory with observation. Every faint galaxy we find or don't find helps refine our picture of the cosmos. So the next time you gaze at the night sky, remember, the universe might be hiding far more than it reveals. And those missing dwarfs, they could hold the secret to how everything, including our own galaxy, came to be. Just when we thought the early universe couldn't get any stranger, along come the ultimate cosmic outliers, galaxies so bizarre they've earned the nickname impossible monsters. These are the ultra-luminous infrared galaxies, or ULIRG for short, and they shine with the brightness of trillions of suns, yet radiate almost all their light in infrared. What makes them truly baffling is how they defy the very laws of star formation we thought we understood. Here's the puzzle. A typical galaxy like our Milky Way forms stars at a leisurely pace, maybe 1 or 2 new stars per year. But ULIRG, they're cosmic factories churning out thousands of stars annually, cramming what should take billions of years into just a fraction of that time. The energy they release is staggering, equivalent to the output of entire clusters of galaxies packed into a single, chaotic system. So what's powering these luminous beasts? Astronomers are locked in a heated debate. One camp argues that ULIRG are home to the most extreme stellar nurseries ever seen, regions where gas collapses into stars at breakneck speed, creating dazzling bursts of newborn suns. In these dense, turbulent environments, stars form so close together that their combined glow heats surrounding dust, which then re-emits the energy as infrared light. But there's a rival explanation, and it's just as wild. Some scientists believe the true engines of ULIRG are supermassive black holes hidden deep within these galaxies. As gas spirals into these black holes, it heats up to unimaginable temperatures, unleashing torrents of energy that outshine every star in the galaxy combined. The dust surrounding these active black holes absorbs their fierce radiation and re-emits it as infrared, masking the true source of power. The twist: it might not be an either-or scenario. Some ULIRG could be driven by both, a catastrophic cosmic partnership where frenzied star formation and ravenous black holes work in tandem. This dual powerhouse model would explain why these galaxies are so exceptionally bright, with each process amplifying the other. And here's where things get even weirder. ULIRG weren't supposed to exist in the early universe. Star formation on this scale requires vast amounts of gas, yet models suggest the primordial cosmos didn't have enough raw material to fuel such prodigious output. Their very existence forces us to reconsider how quickly gas could accumulate in the first billion years after the Big Bang. What's at stake? Understanding ULIRG isn't just about solving a cosmic curiosity, it's about rewriting the story of how galaxies evolve. If black holes dominate, it suggests these monsters were fleeting phases in galaxy growth, their brilliance snuffed out as they consumed their fuel. But if star formation is the key, it hints at an era when galaxies could assemble stars at rates we've never seen since. The next generation of telescopes, like the James Webb Space Telescope, is already peeling back the dusty shrouds of these enigmatic giants. With every observation, we're getting closer to answering whether ULIRG are the product of stellar frenzy, black hole gluttony, or something even more extraordinary. One thing's certain: the early universe was far more violent and exuberant than we ever imagined. And as we'll soon see, the mysteries only deepen when we encounter the universe's earliest supermassive black holes, objects so massive and so ancient they challenge our very understanding of time itself. But the cosmic surprises don't end there. If ULIRGs stretched our understanding of star formation, the universe's first supermassive black holes tear it apart completely. These are not just any black holes, they're behemoths, some weighing in at billions of times the mass of our Sun, and they appeared shockingly soon after the Big Bang. The real puzzle: we've spotted quasars, bright disks of matter swirling around these ancient black holes, already fully formed when the universe was less than 700 million years old. That's like finding a skyscraper in the middle of a wilderness we thought was still untouched. So how did these monsters grow so big, so fast? The leading theory points to something called direct collapse black holes. Picture this: in the early universe, vast clouds of pure hydrogen gas could have collapsed under their own gravity, bypassing the usual star formation process entirely. Instead of fragmenting into stars, these clouds would have imploded into a single, massive black hole, a seed weighing tens or even hundreds of thousands of solar masses right from the start. With that kind of head start feeding on the dense gas around them, these black holes could have ballooned to supermassive sizes in a cosmic blink. But there's another contender: rapid mergers. Imagine a crowded dance floor where smaller black holes keep colliding and merging, building mass at an incredible rate. In the dense environments of early protogalaxies, this could have happened far faster than we once thought possible. The problem: even with frequent mergers, it's tough to explain how black holes reached billions of solar masses in such a short time. Some researchers suggest these mergers might have been supercharged, perhaps by violent interactions with gas-rich surroundings or even exotic physics we haven't yet uncovered. Here's where things get really mind-bending. The existence of these early supermassive black holes challenges not just our ideas about black hole growth, but the entire timeline of cosmic evolution. The standard model assumes black holes grow gradually, feasting on gas and the occasional star over billions of years. Yet these ancient giants suggest something far more dramatic: a universe where black holes could have formed and grown to maturity in less than a tenth of that time. What's at stake? If direct collapse is the answer, it would mean the first supermassive black holes were born big, rewriting the rules for how structures form in the universe. If mergers dominated, it would imply the early cosmos was far more chaotic and crowded than our simulations predict. Either way, their existence forces us to reconsider how quickly cosmic structures can assemble, and whether we're missing a critical piece of physics in our equations. The hunt for clues is on. Telescopes like the James Webb Space Telescope are now peering back to this era, searching for the faint glows of gas falling into these primordial black holes. Others are scanning for gravitational waves, ripples in space-time, that might reveal violent mergers from the universe's first billion years. Every new detection brings us closer to solving this cosmic riddle. One thing is certain: the early universe didn't play by the rules we thought we knew. And as we'll see next, the mysteries only multiply when we turn our gaze to the invisible scaffolding of the cosmos, the great cosmic web. Now let's step back and look at the bigger picture literally. If the first supermassive black holes are the universe's early monsters, then the great cosmic web is the invisible scaffolding that holds everything together. Picture the cosmos not as a random scatter of galaxies, but as a vast, intricate network, like the veins of a leaf or neurons in a brain. This is the cosmic web, filaments of dark matter stretching across billions of light years, with galaxies clustering along them like pearls on a string. The real magic lies in how this web shaped the first galaxies. Simulations show that in the early universe, dark matter, that mysterious, invisible stuff making up most of the universe's mass, began clumping together under gravity's pull. These clumps formed long, thread-like filaments, with the densest intersections becoming the birthplaces of the first stars and galaxies. It's as if the universe had a blueprint, an invisible skeleton guiding where cosmic structures would grow. But here's the catch: While modern telescopes can map the cosmic web in the relatively nearby universe, seeing its infancy, those first fragile threads from the cosmic dawn, is incredibly tough. The reason: the earliest filaments were made of pristine hydrogen and dark matter, with no stars to light them up. They are ghosts in the darkness, visible only indirectly through their gravitational effects on surrounding matter or the faint glow of gas they once contained. Scientists have turned to supercomputers to crack this puzzle. By simulating the universe's evolution from the Big Bang forward, these models reveal how dark matter filaments funneled gas into the first proto-galaxies. The simulations show something extraordinary. Without this web, galaxies might never have formed at all. The filaments acted as cosmic highways, channeling raw material to growing structures with astonishing efficiency. Yet, even with these simulations, mysteries remain. For instance, why do some early galaxies appear misaligned with the web's predicted structure? Some theories suggest turbulence in the primordial gas or the explosive influence of the first supernova could have knocked galaxies off course. Others propose that dark matter itself might behave differently on these vast scales, interacting in ways we don't yet understand. The hunt for the cosmic web's origins is pushing telescopes to their limits. Instruments like the James Webb Space Telescope are searching for the faint traces of hydrogen gas illuminated by the first galaxies, hoping to trace the web's outline. Meanwhile, radio astronomers are tuning into the faint whispers of neutral hydrogen, using the 21-centimeter line, a fingerprint left over from the universe's infancy. Every new dataset brings us closer to seeing this hidden architecture in its earliest stages. What makes this so thrilling is the sheer scale of discovery still ahead. Mapping the cosmic web's beginnings isn't just about understanding galaxies, it's about decoding the universe's hidden rules. And as we'll see next, even the smallest elements in this cosmic drama hold surprises, like the puzzling case of missing lithium in the oldest stars. Now let's zoom in from the vast cosmic web to something far smaller but just as puzzling: lithium, the third element in the periodic table. You'd think something so light and simple wouldn't cause much trouble, but when it comes to the oldest stars in the universe, lithium is at the center of a cosmic detective story. Here's the mystery. According to the Big Bang theory, specific amounts of light elements like hydrogen, helium, and lithium should have been forged in the universe's first few minutes. For the most part, hydrogen and helium match predictions perfectly, but lithium, observations of ancient stars, those nearly as old as the universe itself, show only about 1/3 the lithium expected. It's as if someone swiped 2/3 of the universe's lithium stash, and we have no idea how or why. This isn't just a tiny discrepancy. It's a gap that forces us to rethink either our understanding of the early universe or how stars behave. One possibility is that our models of the Big Bang are missing something, perhaps an unknown particle or interaction that altered lithium production. Some theories even suggest dark matter could have played a role, annihilating or decaying in ways that suppressed lithium formation. But there's another suspect: the stars themselves. Ancient stars, known as population 2 stars, have deep convection zones. Think of them as giant mixing bowls that can drag material from the surface down to scorching inner layers where lithium gets destroyed. If these stars burn through their lithium over billions of years, that could explain the shortage. Yet some studies show that even younger stars with less mixing still have less lithium than expected, leaving the mystery wide open. Then there's the wild card: cosmic rays. High-energy particles zipping through space can smash into heavier atoms, breaking them apart and creating lithium as a byproduct. If this process added extra lithium later, it might mask the original deficit, but calculations suggest this wouldn't be enough to fill the gap, leaving us back at square one. The plot thickens when we look at the universe's lithium in different forms. Most measurements focus on lithium-7, the stable isotope, but there's also lithium-6. Some studies hint that lithium-6 might be even more scarce relative to predictions, adding another layer to the puzzle. Could an unknown nuclear process in the early universe have skewed the ratios? Or did some violent event, like waves of supernova, selectively destroy one type of lithium? What makes this so fascinating is that lithium is a cosmic breadcrumb, a tiny clue with huge implications. If the problem lies with the Big Bang, it could mean our entire picture of the universe's first minutes needs adjusting. If stars are to blame, it reveals new complexities in how they evolve. And if it's something entirely unexpected, well, that's where the real fun begins. As telescopes like the Extremely Large Telescope come online, scientists hope to measure lithium in even older, more pristine stars, tracing the element's journey back to cosmic dawn. Until then, the lithium problem remains a tantalizing gap in our cosmic story, one that reminds us how much we still have to learn about the universe's earliest moments. And speaking of cosmic ingredients, this mystery ties perfectly into our next head-scratcher: how the first stars forged the universe's heavy elements, seeding the cosmos with the building blocks of everything we see today. Shifting our gaze from lithium to heavier elements, we enter an era where the first stars changed the universe forever. These colossal population 3 stars didn't just burn hydrogen and helium, they were the universe's first alchemists, transforming simple atoms into the ingredients for everything we know. Imagine a star hundreds of times more massive than our Sun, blazing at temperatures so extreme that it could fuse atoms in ways modern stars never can. Unlike today's stars, which are polluted with traces of heavier elements, population 3 stars were pristine pure hydrogen and helium. This purity made their nuclear furnaces far more efficient, allowing them to create elements like carbon, oxygen, and even iron in their cores. But here's the twist: when these giants died, they didn't go quietly. Their supernovas were unlike anything we see now, violent, asymmetrical explosions that blasted newly forged metals into the cosmos. What made these supernovas so different? For starters, the lack of heavier elements meant stars cooled differently as they collapsed, leading to bizarre, ultra-energetic explosions. Some models suggest these stars might have died in pair instability supernovas, where matter and antimatter particles spontaneously form in the core, triggering a runaway reaction that obliterates the entire star, leaving no black hole behind. Others propose hypernovas, explosions 100 times more energetic than typical supernovas, capable of flinging metals across vast distances. These cataclysms didn't just spread elements, they shaped how future galaxies would form. This is where the cosmic seeding begins. Those first heavy elements didn't just linger in space, they became the raw material for the next generation of stars, planets, and eventually us. But here's the puzzle: when we look at ancient stars from later generations, their metal patterns don't quite match what we'd expect from standard supernovas. Some have bizarrely high amounts of carbon relative to iron, while others show strange zinc or cobalt abundances. The explanation: population 3 stars didn't all explode the same way. Some might have shed outer layers rich in lighter elements before dying, while others collapsed directly into black holes, trapping heavier metals inside. The evidence hides in the oldest stars we can find, those with barely a sprinkle of metals. These celestial fossils preserve the chemical fingerprints of those first explosions. Take E1 327-2326, a star in the Milky Way's halo with an iron content millions of times lower than the Sun's. Its bizarre mix of elements suggests it formed from the debris of a single population 3 supernova. Then there's the star SMSS 0313-6708, which has almost no iron but surprising amounts of carbon and nitrogen, a possible relic of a star that died in a unique, poorly understood explosion. The search for these first metals isn't just about chemistry, it's about understanding how the universe grew up. Those initial bursts of heavy elements dictated how quickly galaxies could cool, collapse, and form new stars. Too few metals and gas couldn't condense efficiently. Too many, and radiation from younger stars might have blown material apart. It's a delicate balance that likely shaped the timeline of cosmic history. As we piece together this story, new questions emerge. Did some population 3 stars collapse quietly into black holes, locking away their metals forever? Could their remnants still drift unseen in our galaxy's halo? And how did these first heavy elements influence the birth of the first planets? One thing's certain, without those pioneering stars and their explosive deaths, the universe would lack the diversity we see today. No rocky planets, no organic molecules, no chemistry complex enough for life. This brings us to another enigma: how these early metals interacted with the universe's growing structures. A dance we'll explore next as we examine the haunting Lyman alpha forest and its clues about the first galaxies. Now, let's step into the shadows of the early universe, where light itself becomes a map to the past. When astronomers peer at the most distant quasars' lighthouses of the young cosmos, they don't just see brilliant points of light. They detect something far stranger: a forest of dark lines slicing through the quasar's spectrum, each one a clue to the hydrogen gas that once filled the universe. This is the Lyman alpha forest, a cosmic barcode holding secrets about the era when galaxies were just beginning to take shape. Here's how it works. As quasar light journeys across billions of light years, it passes through clouds of neutral hydrogen gas. Each cloud absorbs a specific wavelength of light called the Lyman alpha line, imprinting a dark mark on the quasar's spectrum. The farther away the cloud, the more the universe has stretched, shifting its absorption line toward redder wavelengths. The result: a dense thicket of lines, some close together, others spread apart, painting a timeline of hydrogen distribution from the present back to when the universe was less than 1 billion years old. But this forest isn't just a record of gas, it's a snapshot of cosmic evolution. Where the lines cluster tightly, they trace dense filaments of the cosmic web, the scaffolding upon which galaxies grew. Gaps in the forest, meanwhile, reveal ionized bubbles blasted clear by the first stars and galaxies. By studying these patterns, astronomers can reconstruct how the universe transformed from a dark, neutral sea into the structured cosmos we see today. Yet there's a tantalizing gap in the story. While the Lyman alpha forest maps hydrogen clouds with incredible precision, it struggles to reveal the very first stars. Why? Because those earliest stars were so hot and energetic that their ultraviolet radiation ionized vast regions of hydrogen, erasing the neutral gas that would have left absorption lines. It's like trying to study a wildfire by examining the charred ground it left behind. You see the aftermath, not the flame itself. This creates a paradox. The same process that makes the Lyman alpha forest so valuable, its ability to trace hydrogen, also means it's blind to the stars responsible for ionizing that hydrogen. To catch glimpses of population 3, astronomers must hunt for indirect clues. For example, some quasar spectra show unusually thick absorption lines, hinting at pockets of pristine gas that might have lingered near early stars. Others reveal regions with abrupt transitions from neutral to ionized gas, possibly marking the edges of bubbles carved out by the first galaxies. The forest also hides surprises about cosmic chemistry. In rare cases, heavier elements like carbon or silicon appear in the absorption lines, suggesting that some early galaxies polluted their surroundings faster than expected. These metal lines are like finding footprints in a primordial jungle, evidence that star formation and supernovas were already reshaping the cosmos even before the forest's hydrogen was fully ionized. New tools are sharpening our view. The James Webb Space Telescope can study infrared light from quasars even more distant than those visible from Earth, probing deeper into the forest's roots. Meanwhile, supercomputer simulations now recreate how the first stars and galaxies would have altered the hydrogen landscape, letting astronomers test theories against the real forest's tangled patterns. The Lyman Alpha Forest reminds us that the universe's history isn't just written in starlight. Sometimes the most revealing chapters are found in the shadows, the silent absorption lines that whisper how emptiness gave way to structure and how the first sparks of light changed everything. Next, we'll confront an anomaly that defies expectations, a galaxy far too mature for its age, lurking at the edge of time itself. Now, shifting our gaze to one of the most baffling discoveries in the cosmic frontier, we encounter GNZ 11, an object that shouldn't exist, yet shines defiantly from the edge of time itself. This galaxy, captured by the Hubble Space Telescope, holds the title of the most distant galaxy ever observed, a staggering 13.4 billion light-years away. What makes it impossible? GNZ 11 isn't just old, it's shockingly mature for its age, appearing fully formed when the universe was a mere 400 million years old. To grasp why this baffles astronomers, picture a toddler solving advanced calculus. Current models suggest galaxies start small, growing gradually as they merge and accumulate gas over billions of years. But GNZ 11 breaks all the rules. It's already massive, churning out stars at a rate 20 times faster than our Milky Way does today. Its brightness suggests it harbors a population of stars that must have formed incredibly early, cramming what should have been a slow cosmic process into a blink of universal time. How did it grow so fast? One theory points to an unusually dense pocket of dark matter in the early universe, where gravity could have pulled in gas at breakneck speed. Another possibility is that GNZ 11 stars formed with almost no heavy elements, making them far more luminous than modern stars, but even these explanations strain credibility. For a galaxy this mature to exist so soon after the Big Bang, star formation would have needed to start almost immediately after the first stars flickered to life, leaving virtually no time for the gradual buildup we see in later epochs. The galaxy's structure adds another layer of mystery. High-resolution observations reveal a compact, disk-like shape, not the chaotic clump expected in such an ancient object. This implies stable rotation and organized motion, features that typically take much longer to develop. Some researchers speculate GNZ 11 might be the core of what would eventually become a giant elliptical galaxy, but even that requires a head start defying conventional timelines. Perhaps the most tantalizing clue lies in its color. GNZ 11 glows unusually bright in ultraviolet light, a hallmark of intense star formation. Yet this same light carries subtle fingerprints suggesting the galaxy is already enriched with heavy elements, carbon, oxygen, and nitrogen forged in the hearts of earlier stars. If confirmed, this means GNZ 11 didn't just form stars rapidly. It also hosted generations of supernovas polluting its gas with metals in record time. The implications ripple across astrophysics. If galaxies like GNZ 11 are common, our models of cosmic dawn may need a complete overhaul. Perhaps the first galaxies formed under conditions far more extreme than simulations predict, with star formation operating at efficiencies we can't yet explain. Or maybe the universe's infancy played by different rules altogether, with physical constants or dark matter behaviors we haven't accounted for. New observations could crack the case. The James Webb Space Telescope has already trained its mirrors on GNZ 11, probing its chemistry and star-forming regions in unprecedented detail. Early data hints at even more surprises, including possible evidence of population 3 stars lurking in its outskirts. Meanwhile, astronomers scan other corners of the sky for similar cosmic anomalies, wondering if GNZ 11 is a rare exception, or a sign that we've underestimated the universe's ability to build complexity at lightning speed. GNZ 11 stands as a humbling reminder that the cosmos often defies our neat categorizations. Just when we think we understand the rules of galaxy growth, the universe throws us a curveball, a fully formed city of stars where we expected only scattered campfires. Next, we'll delve into another puzzle: why the hunt for truly pristine stars, untouched by heavy elements, has come up empty despite decades of searching. Now, turning our attention to another cosmic enigma, we confront the baffling absence of metal-free stars, those elusive celestial objects that should have been the universe's firstborn. Theory tells us the earliest stars, known as Population 3, were forged from nothing but hydrogen and helium, the pristine elements left behind by the Big Bang. Yet after decades of scanning the skies, astronomers have found 0 stars completely devoid of heavier elements. This glaring gap in our cosmic record raises a pressing question: where did all the pure stars go? One possibility is tragically simple: they might not exist anymore. Population 3 stars were likely monstrous in size, hundreds of times more massive than our Sun, burning ferociously and dying young in spectacular supernovas. Their short lifespans, just a few million years, would have left little trace, their ashes scattered and recycled into later generations of stars. But even if the original stars are gone, their remnants should linger. Supernova explosions from these behemoths would have seeded surrounding gas clouds with traces of metals, so finding stars with even minuscule amounts of heavy elements could point to their existence. Yet the cleanest stars we've found, like the ancient SMSS J03 1300 36,670,839, still contain faint whispers of calcium and iron. This leads to another puzzle: perhaps pollution is inevitable. In the chaotic early universe, supernova winds and galactic mergers could have contaminated even the most isolated pockets of pristine gas. Imagine a drop of ink in a glass of water. No matter how small, it eventually spreads. Similarly, the first heavy elements once created might have permeated every corner of the cosmos, leaving no star untouched. Supporting this, computer simulations show that turbulence from early star formation could have mixed metals far more efficiently than we assumed, making truly metal-free stars a fleeting phenomenon. But some scientists argue the problem lies not in the stars themselves, but in our tools. Detecting a pure hydrogen-helium star is like searching for a single white grain of sand on a sunlit beach. Current telescopes struggle to identify stars with metal levels below 1/10,000th of the Sun's abundance. The light signatures of these objects, lacking the telltale absorption lines of heavy elements, could blend into the noise of cosmic background radiation. New instruments like the James Webb Space Telescope and upcoming 30-meter class observatories might finally pierce this veil, spotting ultra-faint stars in the Milky Way's halo or neighboring dwarf galaxies where such relics could still hide. The stakes are high. Finding even one metal-free star would revolutionize our understanding of cosmic dawn. These stars were the furnaces that forged the first heavy elements, the architects of everything from planets to life. Their absence forces us to reconsider fundamental assumptions. Did Population 3 stars form differently than we think? Could some have avoided pollution by forming in isolated voids? Or does their missing chemistry hint at exotic physics, like interactions with dark matter that altered their evolution? For now, the hunt continues. Astronomers sift through data from sky surveys, hoping to spot a star whose light carries no fingerprint of metals. Others model the intricate dance of gas and radiation in the early universe, testing whether pristine stars could have existed long enough to leave traces. Whatever the answer, this cosmic detective story reminds us that sometimes what we don't find teaches us just as much as what we do. Next, we'll explore another tantalizing question. Could the first stars have had companions, sparking the birth of binary systems in the universe's infancy? Now, let's shift our gaze to another fascinating puzzle: the possibility that the universe's first stars weren't solitary giants, but instead danced in pairs. Could the earliest stars have had companions, forming binary systems in the cosmic dawn? This question isn't just about stellar partnerships. It holds clues to how planets, and perhaps even life, eventually emerged. Binary stars are commonplace today, Roughly half of all Sun-like stars in the modern universe have at least one stellar companion, but when we rewind to the beginning, the rules might have been different. Population 3 stars born from pure hydrogen and helium were likely far more massive than today's stars, with gravitational collapses that could have favored single stars. However, recent simulations suggest turbulence in primordial gas clouds might have splintered them into multiple fragments, creating the first binary or even triple systems. Imagine two behemoths, each hundreds of times the Sun's mass, orbiting one another in a deadly embrace. Their fierce ultraviolet radiation would have carved vast cavities in the surrounding gas, shaping the environments where future stars formed. If binaries existed, their deaths would have been spectacular. Colliding or merging, these stars could have triggered hypernovas, explosions 10 times more energetic than typical supernovas, spraying heavy elements across vast distances. Even more intriguing, their remnants might have given rise to the first binary black holes. Gravitational wave observatories like LIGO and Virgo have detected black hole mergers with puzzlingly large masses, some exceeding 50 solar masses. Could these be the ancient echoes of population 3 binaries? The implications for planet formation are profound. Today, planets often form in the swirling disks around young stars. But in the early universe, the intense radiation from massive binaries would have vaporized dust grains, making traditional planet building difficult. Yet some theorists propose an alternative: carbon planets. With oxygen scarce in the first stellar generations, carbon-rich debris might have clumped into exotic worlds with diamond cores and tar-like atmospheres. Finding such planets or their remnants could hint at the existence of early binaries. Detecting these primordial pairs directly is nearly impossible. Their light faded billions of years ago. But their gravitational wave signatures could still linger. Future detectors like the Laser Interferometer Space Antenna LISA might catch the faint ripples from mergers of black holes born from the first binaries. Alternatively, astronomers scour metal-poor stars in our galaxy's halo for unusual chemical abundances. A telltale mix of elements like excess carbon or odd neutron capture isotopes could betray the violent deaths of early stellar duos. The hunt for the first binaries is more than cosmic archaeology. It's a chance to test our understanding of star formation under extreme conditions. Did turbulence in pristine gas clouds spin off partners, or were the earliest stars lone wolves? The answer could rewrite how we see the universe's infancy and our own origins. Next, we'll delve into an even more radical idea: that some of the first stars weren't stars at all, but dark matter-powered anomalies glowing in the primordial night. Now, let's venture into one of the most mind-bending theories about the cosmic dawn: the possibility that some of the first objects lighting up the universe weren't stars as we know them, but something far stranger. Picture this: colossal orbs glowing not from nuclear fusion, but from the annihilation of dark matter itself. This radical idea, known as the dark star hypothesis, suggests that in the universe's earliest epochs, dark matter, the invisible, mysterious substance making up most of the cosmos's mass, could have clustered so densely in some regions that it ignited. These hypothetical dark stars would have been fueled not by hydrogen and helium burning in their cores, but by dark matter particles colliding and obliterating each other, releasing immense energy. Unlike regular stars, they wouldn't have flickered out quickly. Some models suggest dark stars could have grown to staggering sizes, up to 10 million times the mass of our Sun and thousands of times brighter, persisting for millions of years before collapsing into black holes. But how do you find an object that might not even emit visible light? The telltale clues could lie in gamma rays, the universe's highest energy light. When dark matter particles annihilate, they should produce gamma rays with distinct energy signatures. Telescopes like the Fermi Gamma Ray Space Telescope have detected unexplained gamma ray excesses from the Milky Way center and nearby dwarf galaxies, regions rich in dark matter. While these signals could have mundane explanations, some scientists speculate they might be the dying breath of ancient dark stars or their remnants. Another piece of the puzzle comes from the cosmic infrared background, a faint glow permeating the universe. Some argue it's brighter than what known galaxies can explain. Could dark stars radiating heat as they devour dark matter account for this excess? Their light would have been redshifted into infrared over billions of years, leaving a subtle fingerprint. Then there's the black hole connection. If dark stars eventually collapsed, they might have seeded the universe's first supermassive black holes far earlier than traditional models allow. Some of the most distant, monstrous black holes we've found, like those powering early quasars, seem too massive to have formed so quickly. Dark stars could offer a shortcut, creating massive black hole seeds in one dramatic implosion. Skeptics point out the challenges. We still don't know the true nature of dark matter, whether it's made of weakly interacting massive particles, actions, or something else entirely. Without knowing how it behaves, predicting dark star signatures remains speculative. Yet the idea persists because it solves so many cosmic riddles at once: odd gamma rays, unexpected infrared light, and impossibly early black holes. The hunt for dark stars isn't just about rewriting stellar astrophysics. It's a potential gateway to finally understanding dark matter itself. If future telescopes like the James Webb or the upcoming Nancy Grace Roman Space Telescope spot an ancient object with the wrong spectrum or inexplicable brightness, it might just be the smoking gun. Until then, dark stars remain a tantalizing what if, reminding us that the early universe might have been even wilder than we imagined. Next, we'll explore another twist in the cosmic dawn saga: the possibility that planets' worlds with skies unlike anything today might have formed around those first unimaginable stars. Turning our gaze to another cosmic puzzle, let's consider whether the universe's earliest stars could have hosted planets' worlds orbiting these primordial giants. Imagine a planet bathed in the eerie glow of a population 3 star, a place where the very chemistry of existence was fundamentally different from anything we know today. The idea of planets forming around these ancient stars challenges everything we understand about planet formation. Normally, planets birth from the dusty debris left over after a star ignites. But population 3 stars were made of pure hydrogen and helium, with no heavy elements like silicon or iron to form rocky cores or icy grains. So how could planets even exist in such an environment? One theory suggests these stars might have had dust-free protoplanetary disks, but not in the way we'd expect. Instead of the familiar swirling clouds of rock and metal, their disks could have been dominated by helium hydride, a simple molecule that might have clumped together under extreme conditions. These clumps could have acted as seeds for protoplanets, growing through collisions until they became massive gas giants, devoid of solid surfaces but rich in exotic chemistry. But what if some of these early worlds weren't just gas? Another startling possibility involves carbon planets. In the final moments of a population 3 star's life, as it exploded in a supernova, it would have forged carbon in its core. If this carbon-rich debris later collapsed into new stars with their own disks, it might have created planets not of rock or gas, but of diamond-like carbon structures. Picture a world with mountains of graphite, rivers of tar, and skies thick with carbon compounds, an alien landscape beyond our wildest sci-fi imaginings. The search for evidence of these first planets is like hunting for ghosts. Any such worlds would have been vaporized or swallowed long ago when their host stars died violent deaths. But astronomers aren't entirely empty-handed. Some of the oldest stars we've found in the Milky Way's halo, like SMSS 0313-6708, contain traces of carbon and other elements that hint at pollution from earlier generations of planets. These chemical fingerprints might be the only relics left of the universe's first planetary systems. Then there's the question of habitability. Could life have arisen on these ancient worlds? It seems unlikely without heavier elements like oxygen or phosphorus. The building blocks of life as we know it would have been scarce. But if even a few population 3 stars lived long enough to enrich their surroundings with metals, perhaps some late-forming planets in their systems could have harbored the precursors of life. It's a tantalizing thought that life's origins might trace back to the ashes of the very first stars. The James Webb Space Telescope could bring us closer to answers. By studying the atmospheres of the oldest known exoplanets, it might detect unusual carbon-to-oxygen ratios that betray their exotic origins, or it could spot unexpected disk structures around distant metal-poor stars, offering clues about how planets form in extreme environments. For now, the existence of population 3 planets remains one of cosmology's great what-ifs. But whether they were diamond worlds, helium giants, or something even stranger, their potential discovery would rewrite not just the history of planets, but the story of how cosmic diversity began. Next, we'll unravel how astronomers are piecing together another piece of the cosmic dawn puzzle, the moment when starlight first pierced the darkness of the early universe. Now, shifting our focus to one of the most fundamental mysteries of all, when exactly did the universe flicker to life with its first starlight? Pinpointing the cosmic dawn's timeline is like trying to read a shadowy chapter of history where the pages keep changing. Astronomers face a thorny debate with 2 key lines of evidence telling seemingly conflicting stories. On one side, we have whispers from the hydrogen clouds of the early universe, captured as faint 21-centimeter radio signals. On the other, there's the light of ancient galaxies spotted by our most powerful telescopes. The problem: these 2 methods disagree by hundreds of millions of years, leaving us to wonder who's got the timeline right. Let's start with the 21-centimeter signals, the universe's own echo from the Dark Ages. As the first stars began to shine, their ultraviolet radiation interacted with the sea of neutral hydrogen filling the cosmos, subtly altering the hydrogen atom's energy states. This left a fingerprint in the form of radio waves at the 21-centimeter wavelength, a ghostly signal we can detect today. Projects like the experiment to detect the global epoch of reionization signature, or edges, claimed to catch this signal in 2018, suggesting stars lit up as early as 180 million years after the Big Bang. But there's a catch. The signal was far stronger than models predicted, sparking skepticism. Was it a revolutionary discovery, or could earthly interference have muddied the data? The controversy remains unresolved. Meanwhile, galaxy surveys paint a different picture. Telescopes like Hubble and James Webb have pushed deeper into space and time, spotting galaxies that existed when the universe was barely 400 million years old, and these galaxies already look mature with complex structures. If stars started shining much earlier, as the 21-centimeter data hints, where are the even older galaxies to prove it? Either they're too faint for our current instruments, or the 21-centimeter signal is telling us something unexpected about how those first stars behaved. Here's where it gets even trickier. Some theorists propose that the earliest stars weren't like the ones we know today. Maybe they formed in isolated pockets, their light too sparse to build galaxies quickly. Or perhaps dark matter played a role, with hypothetical dark stars emitting heat but little visible light, skewing our detection methods. Others suggest that the 21-centimeter signal might be affected by exotic physics, like interactions between dark matter and hydrogen that we don't yet understand. The stakes are high. Nailing down the cosmic dawn's timeline isn't just about fixing a date in a cosmic calendar. It's about understanding how quickly the universe transitioned from simplicity to complexity, how the first seeds of galaxies took root, and whether our models of cosmic evolution need a radical rewrite. Future missions like the Square Kilometre Array, with its unparalleled sensitivity to 21-centimeter waves, or next-generation space telescopes may finally bridge the gap between these conflicting clues. For now, the cosmic dawn remains tantalizingly out of focus. a hazy sunrise where the light we see depends entirely on the lens we use to look. Up next, we'll explore another hidden force shaping the early universe, the mysterious origins of its first magnetic fields. Now, let's turn our attention to an invisible force that quietly shaped the cosmos, the mystery of the universe's first magnetic fields. Picture this, a young universe still in its infancy, yet already threaded with magnetic forces powerful enough to influence the birth of stars and galaxies. But how did these fields emerge from nothingness? Unlike stars or galaxies, magnetism leaves no direct light signature, making it one of the most elusive puzzles in cosmology. One leading theory points to the first generation of stars as cosmic blacksmiths. As these massive stars burned bright and died young, their violent deaths in supernova explosions could have generated turbulent plasma flows. Just like a dynamo in a power plant, these swirling currents may have amplified weak seed fields into the structured magnetism we detect today. Supporters of this idea argue that early stellar winds and supernova remnants acted like cosmic stirrers, churning the primordial gas and weaving magnetic fields into the fabric of space. But here's the twist. Some researchers propose that magnetism existed even before stars, a relic from the Big Bang itself. Quantum fluctuations in the universe's fiery birth could have created faint primordial magnetic fields. Over eons, the expansion of the cosmos stretched these fields across vast distances, while the collapse of gas into galaxies and clusters amplified them further. If true, this would mean magnetism isn't just a byproduct of stars but a fundamental feature of space as ancient as time itself. The debate heats up when we look at the evidence. Observations of distant galaxy clusters reveal magnetic fields threading through them, but their strength and structure don't always match predictions from stellar dynamo models. Meanwhile, the cosmic microwave background, the afterglow of the Big Bang, hides subtle clues. Some scientists claim to have detected faint imprints of primordial magnetism in this radiation, though the signals remain controversial. Complicating matters further is the role of cosmic web filaments. These vast, thread-like structures of dark matter and gas may have acted as magnetic highways, channeling and intensifying fields across the universe. Simulations show that as gas flowed along these filaments during galaxy formation, it could have stretched and twisted weak magnetic fields, boosting their strength. This might explain why even the emptiest regions of space aren't truly devoid of magnetism. So why does this all matter? Magnetic fields aren't just cosmic decorations. They shape how gas collapses into stars, steer cosmic rays, and even influence the growth of supermassive black holes. Unraveling their origins could rewrite our understanding of structure formation in the universe. Future telescopes like the upcoming Square Kilometre Array aim to map these fields in unprecedented detail, potentially settling the debate between primordial and stellar origins. For now, the first magnetic fields remain a ghostly presence felt but not fully seen. Up next, we confront another cosmic paradox, quasars that existed impossibly early, defying our models of black hole growth. Now, let's journey deeper into the cosmic enigma as we encounter quasars that defy time itself, objects so impossibly early that they challenge the very laws of physics. At the heart of this mystery lies J0313-1806, a quasar so distant it blazes from an era just 670 million years after the Big Bang. Yet, its supermassive black hole weighs in at over 1.5 billion times the mass of our Sun. How could such a monster exist in a universe still in its infancy? The problem is simple yet staggering. Black holes grow by swallowing gas and merging with others, but even under ideal conditions, reaching such colossal sizes should take far longer than the cosmos had at that point. Traditional models suggest a supermassive black hole might need nearly 1 billion years to form, yet here we see one fully grown in less time than it takes for most galaxies to even assemble. This cosmic contradiction forces astronomers to rethink black hole origins. and the explanations on the table are as radical as they are fascinating. One possibility is that the first black holes didn't start small. Instead, they might have formed through direct collapse, a process where vast clouds of pristine gas, untouched by heavy elements, collapsed catastrophically under their own gravity, bypassing the star stage entirely. In this scenario, black holes could have been born with masses tens of thousands of times greater than the Sun, giving them a colossal head start. Simulations show that in the dense, early universe, such collapses might have been common, creating black holes primed to feast on the abundant surrounding gas and swell rapidly. But there's another twist. Some theorists propose that early black holes grew faster because the universe was a far more violent place, with galaxies forming in tighter quarters and collisions happening more frequently. Black holes could have gorged on gas-rich mergers, accelerating their growth exponentially. Imagine a cosmic buffet where the plates never empty. This frenzy of feeding might explain how quasars like J0313 became so massive so quickly. Yet the most daring idea of all is that new physics might be at play. Could black holes in the early universe have benefited from unknown mechanisms, perhaps exotic forms of matter, extra dimensions, or even modifications to Einstein's gravity? While these notions remain speculative, their appeal lies in their potential to solve multiple cosmic puzzles at once, from quasars to dark matter. The evidence remains tantalizingly sparse. Observations of J0313's surroundings reveal a galaxy already rich with metals, suggesting rapid star formation and black hole growth occurred side by side. But whether this points to exotic origins or merely an extreme version of known physics is still unclear. Upcoming telescopes like the Vera Rubin Observatory could discover more of these early quasars, mapping their distribution and shedding light on their formation. What makes this mystery so critical is its ripple effect. If black holes could grow impossibly fast, they might have shaped their host galaxies in ways we're only beginning to understand, seeding the cosmic structures we see today. Or if new physics is required, it could rewrite our understanding of gravity itself. As we peel back the layers of this paradox, remember, these quasars aren't just distant lights. They're stopwatches ticking in the dark, measuring whether our models of cosmic evolution need a tweak or a total overhaul. Next, we'll probe the remnants of the universe's first stellar explosions, uncovering why their ghosts remain so elusive. Shifting our gaze from the impossibly early quasars, let's zoom in on the aftermath of the first stellar explosions, the universe's original neutron stars. These incredibly dense remnants, born from the violent deaths of massive stars, pack more mass than our Sun into a city-sized sphere. But how do we find the very first ones, and what can they tell us about the cosmos' turbulent youth? When a massive star exhausts its fuel, it doesn't fade quietly. It collapses inward in a catastrophic supernova, leaving behind either a black hole or a neutron star, a stellar corpse so dense that a teaspoon of its material would weigh 1 billion tons. For the earliest stars, the ones made purely of hydrogen and helium, their deaths would have been even more spectacular. Without heavy elements to help cool their cores, these population 3 stars likely exploded with unmatched ferocity, scattering the first heavy elements into space and birthing neutron stars with unique properties. The challenge: these ancient neutron stars are needles in a cosmic haystack. Unlike black holes, they often reveal themselves through pulsing beams of radiation, spinning like lighthouses as they age. Astronomers hunt for their telltale pulses in the oldest star clusters, relics from the cosmic dawn that might still host these primordial remnants. Imagine a spinning top gradually slowing down. The first neutron stars, now over 13 billion years old, would be faint and slow, their pulses whispers compared to younger counterparts. Yet detecting them could unlock secrets about the universe's first supernova. One clue lies in their composition. Neutron stars from population 3 supernova might contain exotic states of matter not seen today. Think quark-gluon soup or hyperon-packed cores left over from a time before heavy elements existed. Some theories even suggest these early neutron stars could be strange stars, their cores made of strange quarks, a state of matter so extreme it defies earthly physics. If we could find one, its structure would be a time capsule from the universe's first minutes. The search isn't easy. These objects are tiny, dark, and often invisible unless their beams happen to point toward Earth. But new tools are tipping the scales. Radio telescopes like the Square Kilometre Array, set to be the most sensitive ever built, could detect the faintest pulses from these ancient objects. Meanwhile, gravitational wave observatories might catch the ripples from collisions between first-generation neutron stars, events that would reveal their masses and spins, key clues to their origins. Why does this matter? Neutron stars are more than cosmic curiosities. They're the universe's first heavy element factories, forging gold, platinum, and uranium in their collisions. If we can trace their lineage back to the earliest stars, we'd understand how the building blocks of planets and life first spread through space. As we stand on the brink of these discoveries, remember, each faint pulse from the void is an echo of the cosmos' fiery infancy. Up next, we confront a haunting absence: why the debris from those first supernovae seems to have vanished without a trace. Turning our attention to another cosmic puzzle, let's tackle the baffling absence of debris from the very first supernova. If the earliest stars exploded with such violence, where are all the leftovers? The deaths of population 3 stars should have littered space with glowing remnants, expanding clouds of gas and dust rich with the first heavy elements. But when astronomers scan the skies for these ancient fingerprints, they come up startlingly empty. It's like finding evidence of a fireworks display but none of the spent casings. So why is the universe hiding its first supernova wreckage? One clue lies in how these primordial stars lived and died. Unlike modern stars, which contain traces of carbon, oxygen, and other elements, population 3 stars were pure hydrogen and helium. This simplicity made their cores burn hotter and faster, leading to far more explosive deaths. When they finally collapsed, their supernova might have been 100 times more energetic than anything we see today. Instead of leaving behind tidy shells of debris, these titanic blasts could have completely vaporized their surroundings, scattering material so thinly that it became invisible across billions of years. Another possibility: these supernovae were a rare breed called pair instability, explosions so powerful they left no remnant at all. In a normal supernova, the collapsing core rebounds off its own density, creating a neutron star or black hole while ejecting the outer layers. But pair instability events are different. The star's core gets so hot that light itself starts converting into matter, triggering a runaway reaction that obliterates the entire star. No neutron star, no black hole, just a fleeting flash and a spray of heavy elements. If most population 3 stars died this way, it would explain why we can't find their corpses. Then there's the question of time. The first supernova remnants had over 13 billion years to dissipate. Unlike younger debris clouds we see nearby, like the Crab Nebula, these ancient structures would have expanded into near nothingness, their atoms diluted across vast stretches of space. Even if traces remain, today's telescopes might lack the sensitivity to pick them out from the cosmic background. But hope isn't lost. Astronomers are hunting for chemical ghosts, subtle traces of population 3 explosions preserved in later generations of stars. Some ultra-faint dwarf galaxies, relics from the cosmic dawn, show bizarre chemical profiles, lots of elements like oxygen and silicon but almost no iron. This could hint at early supernova that selectively forged lighter elements before vanishing. Other teams scour gas clouds in deep space, searching for pockets enriched with odd ratios of isotopes, possible fossils of first star explosions. The answer might also lie in what we don't see. The absence of certain heavy elements in ancient stars suggests some supernovae were unusually efficient at producing specific materials, another clue to their unique physics. Upcoming telescopes like the Vera Rubin Observatory could spot the faint glow of long-faded remnants, while advanced simulations help reconstruct how these titanic blasts shaped the early cosmos. Every missing remnant is a silent witness to the universe's most violent adolescence. As we piece together their stories, we're not just solving a cosmic cold case, we're uncovering how the first stellar deaths built the groundwork for everything that followed. Next, we'll delve into another ancient enigma, the mysterious origins of the first globular clusters, dense stellar cities that might hold blueprints for early galaxy formation. Now let's shift our gaze to another cosmic relic, the dense, glittering swarms of stars known as globular clusters. These ancient formations, some nearly as old as the universe itself, might hold missing pieces in the puzzle of how galaxies first took shape. Picture a bustling metropolis of stars, hundreds of thousands, sometimes millions, packed into a tight sphere just a few dozen light-years across. Unlike the sprawling spiral arms of modern galaxies, globular clusters are like time capsules, preserving stellar populations that formed when the universe was in its infancy. Yet their chemistry tells a surprising story. Many of these clusters contain stars with unexpected mixes of heavy elements patterns that defy our models of early cosmic evolution. Here's the mystery. If globular clusters were among the first structures to emerge after the cosmic dawn, why don't their stars match predictions? Current theories suggest that early galaxies grew from countless smaller clumps of stars and gas merging together, with globular clusters being some of the sturdiest survivors from that chaotic period. But when astronomers analyze the light from these ancient stars, they find bizarre chemical signatures. Some clusters show stars with wildly varying amounts of elements like oxygen, sodium, or even neutron capture metals, as if multiple generations of stars lived, died, and enriched the same cluster in ways we can't yet explain. One leading idea involves self-enrichment. Imagine a young globular cluster forming from a cloud of pristine gas. The first massive stars ignite, fuse lighter elements, and then explode, seeding the cluster with heavier materials. But instead of dispersing into space, these elements get recycled into new stars within the cluster's dense core. This could create distinct stellar generations with progressively richer chemistry, all within the same tightly bound group. The plot thickens when we compare globular clusters to their proposed building blocks, faint dwarf galaxies. Many ultra-faint dwarfs orbiting the Milky Way have similarly ancient stars, but their chemical patterns are far simpler. This suggests globular clusters experienced unique conditions, perhaps intense bursts of star formation or gravitational interactions that stirred their gas clouds like cosmic batter. Some clusters even show split populations, with one group of stars orbiting in a different direction than the rest, hinting at violent mergers in their past. Then there's the strange case of helium-rich stars. In certain clusters, a fraction of stars burn unusually bright, their spectra revealing excess helium, a trait typically seen in later stellar generations. But how could such stars form in supposedly single-age clusters? One provocative theory suggests that some globular clusters were once far more massive, possibly the cores of shredded dwarf galaxies. Over billions of years, tidal forces stripped away their outer layers, leaving behind only the dense, chemically complex heart. The James Webb Space Telescope is now peering into these stellar time machines, analyzing their faintest members for clues. Early results reveal populations of stars with carbon and nitrogen anomalies, more evidence of turbulent, multi-stage formation. Meanwhile, advanced simulations show that young globular clusters might have hosted thousands of population 3 stars, whose supernova could have ejected enough gas to alter the cluster's chemistry in unpredictable ways. Every globular cluster is like a palimpsest, a cosmic manuscript where older writing has been partially erased and overwritten. Decoding their layered histories doesn't just illuminate their origins, it reveals how the earliest structures seeded the galaxies we see today. Up next, we'll confront an even finer-tuned mystery, the remarkable nuclear reaction that allowed the first stars to forge the building blocks of life itself. Now, let's turn our attention to one of the universe's most delicate balancing acts, a process so precise that without it, life as we know it might never have existed. This is the mystery of the triple alpha problem, the cosmic puzzle of how the first stars forged carbon against staggering odds. Picture the early universe, a place where only the lightest elements, hydrogen, helium, and trace amounts of lithium existed after the Big Bang. For anything heavier to form, stars needed to act as cosmic furnaces, fusing these raw materials into new elements. But here's the catch: the path to creating carbon, the essential backbone of organic molecules, was blocked by a glaring bottleneck. In normal stellar fusion, helium atoms combine in pairs to form beryllium-8. But beryllium-8 is incredibly unstable, lasting just a fraction of a second before it falls apart. For carbon to form, a third helium nucleus must collide with this fleeting beryllium-8 at exactly the right moment. The chances of this happening under typical conditions were astronomically low, so low that early physicists like Fred Hoyle argued the universe must have a special resonance to make it possible. And that's exactly what we've discovered. Hidden within the laws of nuclear physics is a finely tuned energy level in carbon-12, a resonance that allows the triple alpha process to proceed efficiently. When three helium nuclei alpha particles collide, this resonance dramatically boosts the odds of forming stable carbon. Without it, the reaction would fizzle out, leaving the universe devoid of this critical element. What's astonishing is how perfectly matched this resonance is to the conditions inside the first stars. The energy released by fusing helium into beryllium-8, plus the kinetic energy of a third helium nucleus, aligns precisely with carbon-12 resonant state. It's as if the universe had a built-in safety net, ensuring carbon could be synthesized just enough to seed future generations of stars, planets, and life. But the mystery deepens when we consider the timing. Population 3 stars, the universe's first stellar generation, were massive and short-lived. Their cores reached extreme temperatures and pressures, making the triple alpha process far more efficient than in modern stars. Yet even with these ideal conditions, the fine-tuning required for carbon production remains mind-boggling. Alter the resonance energy by just a fraction, and the carbon yield would plummet. Or worse, beryllium-8 might accumulate uncontrollably, leading to runaway reactions that could disrupt the star entirely. This delicate balance doesn't stop at carbon. The same resonance also paves the way for oxygen, another essential ingredient for life. When carbon-12 captures another helium nucleus, it forms oxygen-16, but crucially, oxygen doesn't have a similar resonant state at this energy level. If it did, most carbon would quickly convert to oxygen, leaving too little behind for life's chemistry. Instead, the universe's nuclear properties strike a perfect compromise, producing both elements in proportions that allow complex molecules to emerge. The implications are profound. The triple alpha process isn't just a curiosity of nuclear physics, it's a cosmic prerequisite for life. Without this precise resonance, the first stars might have blazed brilliantly but left behind a sterile universe. Instead, their carbon-rich ashes were recycled into later stars, planets, and ultimately, us. Recent supercomputer simulations show just how sensitive this process is. Tiny variations in the fundamental constants of nature, like the strength of the nuclear force, would disrupt the resonance, making carbon either too rare or too unstable. This has led some scientists to ponder whether our universe is uniquely suited for life, or if other, unseen universes might have entirely different chemical possibilities. As we peer back into the cosmic dawn with telescopes like James Webb, we're not just uncovering how the first stars lived and died, we're decoding the very recipe that made our existence possible. Next, we'll explore another relic of the early universe, the spinning corpses of the first massive stars, and how their vibrations might soon be heard across space and time. Now, let's shift our gaze to the cosmic lighthouses of the early universe, the first pulsars. These rapidly spinning neutron stars are the dense remnants of massive stars that once blazed brightly during the cosmic dawn. But uncovering their origins isn't just about studying stellar corpses. It's about listening to the faint vibrations they left behind, echoes that could soon be detected by the next generation of gravitational wave observatories. Imagine the aftermath of a population 3 stars explosive death. After a supernova tears through the cosmos, all that remains is an ultra-dense core, packed so tightly that a teaspoon of its material would weigh billions of tons on Earth. This neutron star, born spinning at dizzying speeds, becomes a pulsar beaming radiation across space like a cosmic beacon. But here's the puzzle: how did these early pulsars differ from the ones we see today? The first pulsars likely spun hundreds of times per second, far faster than most modern counterparts. Their extreme rotation was fueled by the sheer mass and rapid collapse of their parent stars, which were heavier and purer in composition than stars born later. Without heavier elements to slow their formation, these neutron stars could have revved up to unprecedented speeds, emitting powerful jets of radiation and particles. Yet, despite their brilliance, detecting these ancient pulsars directly is nearly impossible. Their light has been stretched and dimmed by billions of years of cosmic expansion. This is where gravitational waves come in. Unlike light, these ripples in spacetime aren't scattered or absorbed as they travel. Future observatories like the Laser Interferometer Space Antenna or the Einstein Telescope could tune into the vibrations left by the first pulsars. Specifically, they might catch the faint wobbles caused by mountains on a pulsar's surface, tiny imperfections no taller than a few millimeters, but massive enough to warp spacetime as the star spins. Even more intriguing, if 2 neutron stars orbited each other in the early universe, their eventual collision would send gravitational waves roaring across the cosmos, carrying clues about their formation. But why focus on these relics? Because the first pulsars are more than just cosmic curiosities. They're time capsules. Their spin rates, magnetic fields, and even the gravitational waves they emit can reveal the conditions of the early universe. For instance, if we detect pulsars with unusually strong magnetic fields, it could hint that population 3 stars had unique properties like faster rotation or different collapse mechanisms. Alternatively, finding a population of slow-spinning ancient pulsars might suggest that early neutron stars faced more friction from surrounding gas, painting a clearer picture of the primordial cosmic environment. One groundbreaking possibility is detecting a pulsar's ring-down, the moment it settles into its final shape after formation. Like a bell struck by a hammer, a newborn neutron star vibrates at specific frequencies as it releases energy. These vibrations are imprinted in the gravitational wave signal, offering a direct snapshot of the star's interior. If future observatories pick up these signals, we could finally crack open the mystery of how matter behaves under such extreme densities, testing theories that even our most advanced labs can't replicate. The hunt for the first pulsars also ties into one of the biggest questions in astrophysics. Where are all the neutron stars from the cosmic dawn? Given how many massive stars existed back then, we'd expect countless neutron stars to linger in the modern universe. Yet, we've found very few candidates. Some may have been flung out of their galaxies by violent supernova kicks, while others could have faded into obscurity, their beams no longer pointed at Earth. Gravitational waves might be our only chance to find these hidden fossils. As we stand on the brink of this new era of discovery, one thing is certain: the first pulsars hold the keys to understanding the universe's most violent and creative processes. Their whispers, carried across billions of years, are waiting to be heard, and when we finally tune in, we won't just be observing the past, we'll be touching the fabric of spacetime itself. Next, we'll unravel another enigma etched in light: the diffuse glow of the cosmic infrared background, and why it clashes with what our telescopes have captured in the deepest reaches of space. Now, let's turn our attention to a faint but telling whisper from the dawn of time: the cosmic infrared background. This elusive glow is the collective light from the very first stars and galaxies, stretched and dimmed by billions of years of cosmic expansion. Yet, when we compare this faint signal to the galaxies we've actually spotted in deep field images, something doesn't add up. The cosmic infrared background is like the universe's old family photo album, capturing light from countless stars that formed long ago. As these early stars blazed to life, their ultraviolet radiation was absorbed by surrounding hydrogen gas and re-emitted as infrared light. Over time, this light traveled across the cosmos, shifting to even longer wavelengths as space itself expanded. Today, we detect it as a diffuse, all-pervading glow, a relic of that first burst of starlight. But here's the puzzle. When astronomers tally up all the galaxies visible in ultra-deep telescope images like Hubble's frontier fields, the numbers fall short, way short. The combined light from these galaxies accounts for only a fraction of the infrared background's total brightness. So where's the missing light coming from? One possibility is that we're simply missing countless faint, early galaxies, ones too dim or spread out for even our most powerful telescopes to spot. Imagine trying to count fireflies in a foggy field. Some might be so distant or hidden that you only catch glimpses of the brightest few. Similarly, the first galaxies could have been far smaller and more numerous than we've observed, their collective glow adding up to the infrared background we see today. Future telescopes like the James Webb Space Telescope or the upcoming Nancy Grace Roman Space Telescope might finally reveal these hidden builders of the cosmos. Another tantalizing theory involves the very first stars themselves, population 3. These stars, born from pure hydrogen and helium, were likely far more massive and luminous than modern stars. If they burned hot and died young in enormous numbers, their intense radiation could have contributed significantly to the infrared background, even if their individual galaxies are now lost to time. Supporting this idea are peculiar patches in the infrared glow that appear too bright to be explained by known galaxies, hinting at a population of ultra-early, ultra-bright stars we've yet to discover. Then there's the wild card, primordial black holes. Some theorists suggest these mysterious objects, formed in the chaos of the early universe, could have heated surrounding gas as they devoured matter, pumping energy into the cosmic infrared background. While still speculative, this idea adds another layer to the mystery, challenging us to rethink what might have illuminated the young cosmos. The stakes here are high. Solving this discrepancy isn't just about accounting for missing light. It's about testing our entire understanding of how structure formed in the early universe. If we've underestimated the number of small galaxies, it could mean our models of dark matter or star formation need tweaking. If population 3 stars are the culprits, their unique properties could rewrite the story of cosmic dawn. As we peer deeper into this infrared enigma, each clue brings us closer to unraveling the universe's first chapters. And with next-generation telescopes poised to scan the skies with unprecedented sensitivity, we might soon find the missing pieces of this ancient puzzle. Next, we'll delve into the shadowy remnants of the cosmic dawn, the first stellar mass black holes, and how their survival might explain some of modern astronomy's most unexpected discoveries. Now, let's step into the shadows of the cosmic dawn, where the remnants of the first stars may still lurk unseen. These aren't just any black holes, they could be the universe's first stellar mass black holes, forged in the fiery depths of the earliest stars. And here's the astonishing part: some might still be hiding among us today, whispering secrets about dark matter and rewriting the story of how black holes grow. When the first massive stars, population 3, reached the end of their short, brilliant lives, they didn't fade quietly. Instead, they collapsed catastrophically, leaving behind black holes roughly 10 to 100 times the mass of our Sun. Normally, we'd expect these ancient black holes to vanish over time, either by merging with others or evaporating through Hawking radiation. But what if they didn't? What if a fraction survived, drifting through the cosmos like cosmic fossils? This idea isn't just speculative, it could solve two major puzzles at once. First, dark matter. We still don't know what makes up this invisible stuff that outweighs normal matter 5 to 1. But if primordial black holes formed in vast numbers during the cosmic dawn, they could account for at least part of dark matter's mystery. Imagine the universe's first black holes peppered throughout galaxies, their gravity shaping the cosmos while remaining utterly invisible. It's a radical idea, but one that's gained traction as other dark matter candidates remain elusive. Then there's LIGO, the Laser Interferometer Gravitational Wave Observatory. Since 2015, LIGO has been catching ripples in spacetime from colliding black holes. But some of these mergers involve black holes far heavier than expected, with masses clocking in at 30 to 50 times that of our Sun. Where do these chunky black holes come from? One compelling answer: they're relics of the first stars. If population 3 stars were as massive as theories suggest, their black hole remnants would naturally be heftier than those from later generations. LIGO might already be detecting the echoes of the cosmic dawn without us realizing it. But how could these ancient black holes survive for over 13 billion years? The key lies in their environment. In the sparse early universe, chances of collision were slim, allowing many to drift undisturbed. Some might have even been kicked out of their birth galaxies by gravitational interactions, becoming rogue black holes roaming intergalactic space. Others could have nestled into the halos of galaxies, contributing to dark matter's pull while evading detection. The hunt for these primordial black holes is on. Astronomers scour microlensing surveys, looking for brief blips of light as unseen objects warp starlight. Others analyze the cosmic microwave background for subtle scars left by early black holes. And with gravitational wave astronomy advancing, each new merger LIGO detects offers clues. A cluster of unexpectedly massive black hole collisions that could be the smoking gun. What makes this mystery so thrilling is the sheer possibility of discovery. Finding even one primordial black hole would revolutionize our understanding of the universe's infancy, dark matter, and stellar evolution all at once. It's a reminder that the cosmic dawn isn't just a chapter in a history book. Its fingerprints might still be all around us, waiting to be decoded. Next, we'll examine another fragile relic of the first stars, the universe's earliest dust grains, and why their discovery in meteorites has sparked such controversy. Now, let's turn our gaze to something astonishingly small yet monumental in its impact: the first solid particles to form in the universe. Picture this: after the fiery deaths of the earliest stars, their ashes didn't just vanish. Instead, they transformed into something far more enduring: the very first dust grains. These microscopic specks of silicon and carbon were the universe's first steps toward building planets and even life itself. But finding these ancient grains today, that's where the real detective work begins. When population 3 stars exploded as supernova, they didn't just scatter energy, they forged heavy elements in their cores. In the searing heat of these explosions, atoms like silicon and carbon cooled and clung together, forming tiny solid particles no larger than a fraction of a human hair. This wasn't just cosmic debris, it was the raw material for everything to come. Over billions of years, these grains would clump together, forming asteroids, comets, and eventually, the planets orbiting stars like our Sun. The hunt for these primordial grains has led scientists to an unexpected place: meteorites that crash onto Earth. Hidden within these space rocks are presolar grains, microscopic time capsules older than our solar system. How do we know they're from the first stars? Their isotopic signatures tell the story. Unlike particles formed in our solar system, These grains have unusual ratios of elements like carbon-12 and carbon-13, fingerprints that point to their origin in ancient supernova. But here's where controversy ignites. Detecting these grains isn't just difficult, it's riddled with pitfalls. First, contamination is a constant threat. Earth's environment is teeming with modern dust, and distinguishing true primordial grains from earthly imposters requires painstaking analysis. Then there's the problem of rarity. Even in the most pristine meteorites, these grains make up less than 1 in a million particles. Scientists must sift through mountains of data to find a handful of candidates. The debate deepens when we consider how these grains survived. The early universe was a violent place, filled with radiation and shocks that should have obliterated delicate dust. Yet some endured. Did they form in cooler, shielded pockets of supernova remnants, or were they protected by being locked inside larger structures early on? Each hypothesis challenges our understanding of how dust behaves under extreme conditions. Perhaps the most contentious claim is that some of these grains might predate even population 3 stars. A handful of meteoritic particles have isotopic ratios so exotic they might originate from an entirely unknown class of ancient stellar objects, stars that lived and died before the cosmic dawn we think we know. If confirmed, this would rewrite the timeline of the universe's chemical evolution. Why does this all matter? Because dust is more than just cosmic clutter. It's the bridge between the death of stars and the birth of planets. Those first grains absorbed starlight, helping cool gas clouds so they could collapse into new stars. They carried the first complex molecules through space, seeding the universe with the ingredients for chemistry. Without them, Earth and we might never have existed. The next mystery takes us from the microscopic to the colossal, as we explore ultra-luminous infrared galaxies and the dazzling cosmic puzzles they present. Now prepare to witness the universe's most extreme light show, gamma-ray bursts. These blinding flashes, packing more energy in seconds than our sun will emit in its entire lifetime, were likely among the first cosmic fireworks after the birth of stars. But were they creators or destroyers in the early universe? The answer might reshape our understanding of cosmic dawn. Gamma-ray bursts fall into 2 categories. Short bursts last less than 2 seconds and are thought to come from colliding neutron stars. But the ones that interest us here are the long bursts lasting minutes or even hours. These are linked to the deaths of massive stars, exactly the kind of behemoths that dominated the early universe. When a population 3 star, hundreds of times heavier than our sun, exhausted its fuel, it didn't just fade away. Its core collapsed into a black hole, and twin jets of plasma shot outward at nearly the speed of light. These jets, piercing through the star's outer layers, produced gamma rays so intense they could outshine 1 million galaxies combined. Here's what makes these early bursts so puzzling. The first stars formed in pristine hydrogen and helium without heavier elements to block their light. That means their death cries, those gamma-ray bursts, could travel astonishingly far, potentially sterilizing entire swaths of the young cosmos. Some models suggest these bursts ionized gas clouds thousands of light years away, preventing them from cooling and collapsing into new stars. In other words, the very explosions that marked the end of massive stars might have stifled the birth of their successors. But there's another side to this story. The same shockwaves that might have suppressed star formation in one region could have triggered it elsewhere. Imagine a gamma-ray burst shockwave slamming into a nearby gas cloud. The intense pressure could compress pockets of gas just enough to kickstart gravitational collapse, forging new stars where none existed before. This duality, destroyer in one place, creator in another, makes gamma-ray bursts one of the most fascinating forces in cosmic evolution. Detecting these ancient bursts is a monumental challenge. The events themselves lasted mere moments, vanishing billions of years ago. What we see today are their afterglows, fading X-ray and radio emissions captured by telescopes like Swift and Fermi. To find bursts from the first stars, we'd need to spot their infrared signatures stretched by the expansion of the universe over eons. The James Webb Space Telescope might be our best hope, scanning the sky for traces of these primordial explosions. The stakes couldn't be higher. If gamma-ray bursts suppressed early star formation, they might explain why some regions of the young universe seem oddly devoid of galaxies. Conversely, if they acted as cosmic catalysts, they could solve the mystery of how star formation spread so rapidly. Either way, these bursts weren't just spectacular sideshows, they were architects shaping the universe's structure. As we move forward, we encounter another enigma tied to the earliest stellar remnants, neutron stars. These ultra-dense leftovers from the first supernova hold secrets about the violent birth of the cosmos itself. Now, let's turn our attention to one of the most dramatic construction projects in cosmic history, the violent dance of merging galaxies. Picture this: in the early universe, galaxies weren't the grand spirals and ellipticals we know today. They were tiny, fragile things, barely holding themselves together amid the chaos of an expanding cosmos. Yet these humble beginnings held the seeds of everything we see now. Imagine two proto-galaxies, each no bigger than a 10,000th of our Milky Way, drifting through the darkness. Their mutual gravity pulls them closer until crash. They collide in a slow-motion wreck that lasts hundreds of millions of years. Unlike the clean, computer-generated simulations we see, real galactic mergers were messy. Stars didn't physically collide, space is too vast for that, but their orbits were scrambled like marbles in a spinning jar. Gas clouds slammed together, triggering furious bursts of star formation. Dark matter, invisible yet dominant, wove the galaxies into a new, larger structure. Here's where things get puzzling. Current models predict that mergers should have been constant in the early universe, with swarms of tiny galaxies endlessly crashing together. Yet observations show fewer mergers than expected during cosmic dawn. Why the discrepancy? One theory points to feedback. The energy from those first stars and supernova might have blown gas out of small galaxies, making them less likely to stick together during close encounters. Another idea suggests that dark matter halos, the invisible cocoons surrounding early galaxies, were smoother than we thought, reducing gravitational tug-of-wars. The consequences of these mergers were staggering. A single collision could transform a galaxy's destiny. Some grew massive and stable, like our Milky Way. Others became chaotic ellipticals, where stars orbit in all directions like crazed bees. The mergers also funneled gas toward galactic centers, feeding the supermassive black holes that would eventually power quasars. In fact, without these early pile-ups, the universe might lack the giant galaxies we see today. Detecting these ancient mergers is like finding footprints in cosmic sand. Astronomers look for telltale signs, tidal tails of stars stretched out during collisions, unusual star motions, or bursts of unexpected star formation. The James Webb Space Telescope is now spotting baby galaxies in the act of merging, their shapes distorted by gravitational forces. Each discovery helps us understand why some predictions overshoot the mark, refining our simulations of the universe's youth. What's truly mind-bending is how these events shaped us. The atoms in your body were forged in stars born from galactic mergers billions of years ago. Every massive galaxy, including our own, is a patchwork quilt stitched together by ancient crashes. Yet the story isn't over. Our Milky Way is on course to collide with Andromeda in 4 billion years, proving that the cosmic construction zone never truly closes. As we peer deeper into this puzzle, another mystery awaits, one written in the faint bubbles of ionized gas that the first stars left behind. Now, shifting our gaze to a subtler yet equally profound phenomenon, let's explore how the first stars didn't just light up the cosmos, they sculpted it. These celestial pioneers didn't merely shine, they carved intricate bubbles in the hydrogen fog that filled the early universe, etching their presence into the fabric of space itself. Picture the cosmic dawn as a vast neutral sea of hydrogen atoms, so dense that light couldn't travel far without being absorbed. Then the first stars flickered to life. Their intense ultraviolet radiation blasted nearby hydrogen atoms, stripping away electrons in a process called ionization. Over time, this created expanding bubbles of ionized gas, like clearings in a cosmic forest where light could finally travel freely. These bubbles grew as more stars ignited, eventually merging to end the universe's dark ages in what we call the epoch of reionization. The real puzzle lies in how we've struggled to detect these bubbles directly. Scientists predicted they'd leave a distinctive fingerprint, a dip in the 21-centimeter radio wavelength emitted by neutral hydrogen. As bubbles grew, the contrast between ionized cavities and untouched hydrogen should have created a detectable pattern. But despite decades of searching with radio telescopes like EDGES and SARAS, this signal remains maddeningly elusive. What's hiding these cosmic fingerprints? Several theories emerge. First, the bubbles might have formed more chaotically than models suggest, with overlapping ionization fronts creating a noisy signal that blends into background radiation. Second, extreme temperatures in the early universe could have distorted the hydrogen's radio emission, masking the expected dip. There's even a radical idea that interactions with dark matter particles altered how hydrogen absorbed energy, though this remains speculative. The stakes are high. Catching this signal would be like tuning into the universe's baby monitor, revealing exactly when and how the first stars reshaped their surroundings. New projects like the Square Kilometre Array aim to scan the cosmic dawn with unprecedented precision, hunting for whispers of those first bubbles in the hydrogen sea. Meanwhile, the James Webb Space Telescope provides indirect clues by spotting early galaxies that likely drove reionization. Here's the beautiful irony: these bubbles, now vanished for over 13 billion years, shaped everything that followed. Their growth determined where galaxies could form and how light permeated the cosmos. Even more mind-bending, their elusive radio signal isn't lost. It's still traveling through space, stretched by cosmic expansion into faint microwaves. We just need the right tools to hear it. As we edge closer to solving this cosmic hide-and-seek game, another enigma surfaces, one tied to the ultimate fate of those groundbreaking first stars. But that's a story for next time. Turning our attention to the final cosmic conundrum, we arrive at the ultimate fate of the universe's first stars. These stellar pioneers didn't just vanish without a trace, they left behind ghostly remnants that might still haunt our galaxy today. After their spectacular supernova deaths 13 billion years ago, the remains of population 3 stars could be hiding in plain sight, masquerading as dark matter or lurking as elusive black holes in our Milky Way's halo. Let's consider their possible afterlives. When the most massive first stars exploded, they didn't leave behind ordinary stellar corpses. Their pure hydrogen-helium composition and incredible size, hundreds of times heavier than our Sun, meant their deaths created either unimaginably dense black holes or scattered their enriched guts across space in unique ways. Some theories suggest these black holes didn't just sit idle. They could have grown over eons, becoming the mysterious, intermediate mass black holes that astronomers struggle to explain today. Objects weighing thousands of solar masses, too heavy to form from regular stars, yet too light to be supermassive monsters. Even more intriguing is the dark matter connection. If certain population 3 stars collapsed directly into black holes without supernova, they could account for part of the universe's missing mass. These primordial black holes, some no heavier than an asteroid, might drift through our galactic outskirts right now, invisible except for rare moments when they distort starlight or emit faint Hawking radiation. Teams using Japan's Subaru telescope are scanning the Milky Way's halo for these telltale microlensing events, hoping to catch a ghostly population 3 remnant warping the light of background stars. Other searchers focus on chemical forensics, When the first stars exploded, they seeded space with distinct elemental signatures, unusual ratios of elements like carbon, oxygen, and iron that shouldn't exist in pristine gas. Astronomers hunt for these fingerprints in ancient, metal-poor stars within our galactic halo. Stars like SMSS J031300, 36,670,839, which contains iron levels 1 million times lower than our Sun, might have formed directly from the ashes of a single population 3 supernova. By studying such stellar relics, we're essentially performing cosmic archaeology on the first star's debris. The James Webb Space Telescope adds another tool to this search. By analyzing distant quasars whose light passes through primordial gas clouds, Webb can detect absorption lines matching theoretical population 3 supernova models. Finding such a cloud would be like discovering a preserved crime scene, revealing exactly how these stars died billions of years ago. Meanwhile, gravitational wave observatories like LISA may eventually detect ripples from mergers between primordial black holes, potential remnants of those first stellar generations. Here's what makes this mystery so captivating. Unlike other cosmic puzzles that rely on indirect evidence, population 3 remnants could literally be in our backyard. One might pass through our solar system tomorrow, invisible yet detectable through its gravitational fingerprints. Their existence would solve multiple enigmas at once: the nature of dark matter, the seeds of supermassive black holes, and the universe's chemical evolution. As we close our journey through the 30 greatest mysteries of the cosmic dawn, remember this: the first stars didn't just light up the universe. Their echoes still shape it today, hidden in the darkness between the stars, waiting to be found. And with that, we've explored the full spectrum of cosmic dawn mysteries, from the birth of the first stars to their lingering ghosts. But the story doesn't end here. Every new telescope, every advanced simulation brings us closer to unraveling these ancient secrets. Which mystery fascinates you the most? Let us know in the comments below. And don't forget to subscribe as we continue decoding the universe's greatest puzzles. Until next time, keep looking up. As we wrap up this cosmic journey, let's take a moment to reflect on the staggering mysteries we've explored together. The first stars and galaxies didn't just light up the universe. They left behind puzzles that challenge everything we think we know about space. From the elusive population 3 stars, those cosmic giants made of pure hydrogen and helium, to the shocking maturity of galaxies like GNZ11 appearing impossibly early, each mystery peels back another layer of the universe's hidden history. We've grappled with the cosmic dark ages, that mysterious era when the universe was a silent sea of hydrogen, and wrestled with the reionization puzzle, debating whether stars or black holes ripped apart that primordial fog. Then there's the missing dwarf galaxies, defying dark matter predictions, and the ultra-luminous infrared galaxies that burn brighter than physics should allow. We've stared down quasars shining less than 700 million years after the Big Bang, their existence forcing us to rethink how supermassive black holes grow. The lithium problem nags at us. Why do ancient stars lack this element when the Big Bang says it should be everywhere? And the cosmic web's ghostly filaments, the universe's hidden scaffolding, remain stubbornly difficult to map in its infancy. Consider the impossible: stars powered by dark matter annihilation, planets forming around those first metal-free giants, and neutron stars pulsing from the earliest supernova. We've hunted for the first dust grains in meteorites and traced gamma-ray bursts that might have sterilized or fertilized nearby star nurseries. Every clue leads to more questions. Why don't we see the remnants of population 3 supernova? How did globular clusters, those ancient stellar swarms, form with such unexpected chemistry? And what about the triple alpha problem, that delicate nuclear resonance that allowed carbon and ultimately life to exist? The beauty of these mysteries is that they're not just academic. They're pieces of our origin story. The first stars forged the heavy elements in our bones, their black holes might lurk unseen in our galaxy. Their light, stretched into the infrared, still bathes the cosmos as a faint background glow. And with next-generation telescopes like the Roman Space Observatory coming online, we're on the brink of revelations that could rewrite cosmic history. Imagine peering even further back to the moment when the very first star flickered to life, or catching a gravitational wave from a primordial black hole merger. These aren't just dreams, they're tomorrow's headlines, so tell us, which of these 30 mysteries grips your imagination the most? Is it the dark stars, the missing metal-free giants, or something else entirely? Drop your thoughts in the comments below and let's keep the conversation going. If you've enjoyed this deep dive into the universe's greatest unknowns, don't forget to hit like, subscribe, and ring the bell so you never miss our next cosmic adventure. The universe is full of secrets, and together we'll uncover them one mystery at a time. Until next time, keep exploring, keep wondering, and remember, the night sky isn't just above us. It's within us, written in the atoms of those first, unimaginable stars. Thank you for joining us on this journey to the edge of time. The cosmic dawn's greatest puzzles are waiting, and the next discovery could be yours to make.